Right, so today we are going to discuss two papers, that is 2017 paper MCQ and the structured essay, and the 2016 paper. Right, so let's straight away start with 2017 MCQ paper, because we did 18 and 19 in the class. Since we have done two papers, we can do a little bit fast as well. Okay, right, so let's straight away start working on the questions. Right, so the first question, first MCQ question. Suppose we have an array implementation of a queue class with an array. So that means it's a queue implemented using an array, right? Something like this. Named as data, index from 0 to 9. So that means array has up 0, 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 0 to 9. So that means there's one more. 0 to 9 means there's one more element. Okay, entries from data 5 to data 8 are empty. So that means, so this one is empty, this one is empty, this one is empty, and this one is empty. All other locations are filled. So that means here we have data, here it is empty. Where does the enqueue method place the new entry in the array? So we know that in a queue we have front and rear. Data is entered to the rear, data is taken from the front. Okay, so now there are no data here, but there are data here. Okay, so there are data here. So therefore, where is the front? Usually it is from left to right, right? So what they are trying to do is enqueue. Enqueue means you are inserting data. So therefore, the data will be enqueued at the fifth location. Okay, so the answer must be D. Right. So let's move on to the second one. So if you have any questions, you can ask. Okay, because I need you to be more interactive here, because we are just doing fast paper. Okay. Right. Consider the following expression. Assume that stack key is used to check matching parentheses in the above expression. What is the maximum number of tokens? So remember, what they ask is maximum number of tokens. Okay, maximum number of tokens that will be appear in the stack during the matching parentheses process. So in matching parentheses, what we are supposed to do, when there is an opening bracket, we have to push it to the stack. When there is a closing bracket, we want to pop one and check whether it is a matching one. If it is not a matching one, we have to stop it. If it is a matching one, we can keep doing this, right, until we reach the end of the expression. So when we reach the end of the expression, we must not have any parentheses left in the stack. And also, if we are running out of the stack elements, or there is an underflow error before we reach to the end, then that also means there is something wrong. Okay, right, so let's do it. So no parenthesis, no parenthesis. Now we have one parenthesis here, so the stack will have that particular parenthesis. Then we have another parenthesis here, so that parenthesis or the bracket will also be there. Then we have closing bracket, so that means you have to take one out, right? So this will be taken out. Then we have to check with whether they are matching. Yes, they are matching. Then that means we can proceed. Now we have another starting bracket, so now it will be push. It will be push. Then we have another bracket, right? Third bracket, so it will also be push. Then we have closing bracket. Now we have to take one. So when we take one, we are removing this one. Then we have to check whether that bracket is same as no. So that is yeah. So we have to check whether that bracket is same as this kind of bracket. But now you can see they are not matching. So what we have is a curly bracket, starting bracket in the stack. But what we have here is the normal bracket. So that means they are not matching. So that means we have to stop. We have to stop saying that this is not valid. Okay. So then what is the maximum number of tokens in the stack? It's 3. It's 3 because we don't have to process beyond that, because we have found that it is not a valid expression, so we can stop it. So therefore answer must be C, right? Answer must be C. Now let's see whether the answer is correct. Yeah, answer is C. So if you have any doubt, you can ask, okay? Because that is the idea behind this particular session. Clarify all your doubts. So if I can, I will try to clarify all your doubts as much as possible. Okay, right. So now let's move on. If you don't have any questions, we can move on. The third one: structure of a list node used for linked list implementation is as follows. Right, this is a normal single linked list. We have the data part, which is int value, and it is linked into a next node. Okay. Assume that the list with element 54321 is needed to create the above nodes. Right? 54321 needs to be created in the above nodes. What are the commands that are not necessary for the above operation? So that means what they expect is us to create linked list like this. So that is, first link node must be having the value 5, and then it must be having 3, then it must be having uh, 5 4, sorry, 5 4 3 2 and 1. So that is requirement, and this must be pointing to a null. Right. Assume that the list with 54321 is needed to create the above nodes. What are the commands that are not necessary for that operation? Following lines are already being created. So L new node. So that means so there's a new node created, and they call it L, and the value is 5, and the value is 5. Now we want to create other nodes like 4 3 2 1, etc. Okay, 4 3 2 1, etc. Now let's see what are the possible answers, right? So what they ask is that are not necessary for the operation. That means illegal or not necessary statements we want to find. Okay, now let's take one by one. First one, L dot next equal new node. So this is my L. Uh, in order to create this one, I have to do something like that, right? So this is using the L node. We are going to create another node. So then we have to say L dot next, which is a reference variable, right? So therefore it can be used to create a new node. So that is correct. That is correct. So that we have to do, right? Because then only we are creating this second node. Okay. So that we need, right? That we need. So what about the next one? L dot next dot next dot next. Actually, what we are supposed to do is supposed to do L dot next equal new node. Then I will write down the steps actually. Then we can easily figure it out what are the not necessary ones. Okay. So what we now, since we have only this particular line, so the next line would be uh, L dot next equal new node. So that means we are creating uh, this particular uh, node. Okay. Then we have to say that L dot next and its data, right? So remember they call it value, and they call it value. Next value must be 4. Now we are done with this portion, right? This portion. Then we have to create this particular node, that is L dot next equal new node. So if you are familiar with object oriented programming, you can understand. Then we have to say L dot next dot value equal 3. Okay, so now then we have done up to this point. Then we have to say L dot next dot next dot next equal new node. So that means we are creating this particular node. Then again we have to set that value. Then again we have to do one more. Then again we have to set the value. Now those are the things we are supposed to do. Okay. Right. Now let's see. Obviously the first one is correct. Actually what we need is a wrong one. We'll mark the first one. What about the next one? L dot next dot next dot next. So L dot next dot next dot next means L dot next dot next dot next. So that means it must be having the value 2. Right? It must be having the value 2 because that is the next step I should have been written. L dot next dot next dot next dot value, it should have been 2, but this says value is 1, right? Value is 1, so therefore that is wrong, right? That is wrong, right? Third value, L dot next value equal 4, right? So that is correct, right? So L dot next must be 4, so that is exactly the statement. Yeah, that is correct one. L dot next equal new node. Yeah, we have to create like that, right? L dot next. So this one L dot next equal new node. Yeah, we have to create that. So right. So that is basically creating this particular node. Yeah. So that is needed. E L dot next value equal new node. No, that is wrong. So this is int variable, int reference variable. So for that you can't assign a node object. So value must have been something like 5 or whatever. So therefore that is wrong. So what they ask is the wrong answers. So the answer must be B and E. Okay, B and E. So let's see the answers. So if you have any questions or need clarification, you have to ask. Yeah, B and E, right? So that is a purely object oriented preference variables, etc. So if you are not very sure about this, so I have uploaded semester 2 object oriented programming tutorial or the session to the YouTube. You can go through the object oriented. There are about two sessions I have uploaded. So if you are not very sure about these pointing reference variables, etc. So if you go through that, you will better understand. Okay, right. So let's move on. 4. Hand execute to dry run the following pseudocode segment and show the contents of the resulting queue. Okay, so they have given us a code. Now let's see what is the output is going to be. Right. So they are creating a queue object. Right. So they are creating a queue object. Then there's a for loop. Right. There's a for loop. Start from going from 5 to 9, right? So initially I will be 1, then there's an inner loop, it goes from 2 to 5, so therefore initially j will be 2, now we are coming to this particular if condition I mod j. So I mod j initially is 1 mod 2, 1 mod 2, because it's I mod j. Sorry, I made a mistake. I is starting from 5, so not from 1. So therefore initially I is 5, j is starting from 2. So therefore the value must be I mod j must be 5 mod 2, right? If that value is 0, no, 5 mod 2 is not 0, therefore it will go to the else part. So therefore it will be enqueuing the I. Now the queue will have I is 5, right? My queue will have 5 now. Now we are again going back to the inner loop, right? Inner loop. Now j is going to be 3. J is going to be 3. I is still 5. Now it will be I mod j. Again we have to check the I mod j. That will be 5 mod 3. So 5 mod 3 is again 2, not 0. That means again I is going to be enqueue. So I is again 5. I is again 5. Right now, again I is going to be I is going to be, sorry, j is going to be incremented, so it will be now 4. Right, 4. Again it will check I mod j. I is 5. 5 mod 4. Again it is not 0, therefore it will be enqueued. That means the I is going to be enqueued, so I is 5. Again 5 will be enqueued. So actually my queue is going like this. This is my rear. This is my front. Okay, so this is my rear. Right, now again I will be incremented, sorry, j will be incremented to 5, but now when it is 5, this will be as long as j is less than 5, that means I am done with the inner for loop. Now I move into the outer for loop again. Now I will be 6, I will be 6, again j will be initialized to 2. And so this take a lot of time actually. Anyway, let's try to do that. Now again we are going to check I mod j. Now I mod j is 6 mod 2. Yeah, 6 mod 2 is 0. Now it is going to dq. So dq means this 5 is going to be removed. Right? Because that is the real. Right? So then j will be incremented, that is 3. Again it will check 6 mod 3. Again it is 0. That means again there will be a dq. Right? Then again it will be incremented, so now j is going to be 4 again. Now 6 mod 4. Okay, 6 mod 4 is not 0 because there's a remainder of 2. Therefore it will be enqueued. So enqueue in the I, so that means 6 will be enqueued. Okay, right. So now again j will be 5, that means I am going out of the inner for loop again because it's less than 5 only it works. So then I will be incremented, I will be 7. Again j will start from 2. Now it is 7 mod 2. 7 mod 2 is not 0 because there's a remainder, so that means there will be a enqueuing of the I, so that means 7 will be enqueued. Then it is 3, j is 3, again it is not 0, j will be again enqueued, so I will be again enqueued. Then it will be 4, again it is not 0, again it will be enqueued. Right? So that means I is enqueued. Now I am done with the inner loop, I am again going back to the outer loop, now it will be 8. Right? Again j will start from 2, 8 mod 2 is 0, that means there will be a dq. Right? There will be dq. Then 8 mod 3, that is not 0, that means there will be nq. Right? So that means 8 will be enqueued. Okay. Then it is 4. Yes, 8 mod 4 is 0, therefore there will be a dq. Okay. Then it will be 9. Right? I will be 9. The j will be again 2. So 9 mod 2 is not 0. That means it's not 0. That means there will be a nq. Then it will be 3. 9 mod 3 is 0. Therefore there will be a dq. Then it will be 4. 9 mod 4 is not 0. There will be nq. Right? So now it is 9. So now this goes only up to 9 because now it is less than 10. Now we are done. Now our final q must be something like this. Of course, if I didn't make any mistake while doing the hand. Do we have something like this? 99877. Of course, we have it in reverse order. Because sometimes the examiner write the q in reverse order other way. So therefore, I think we can take it. Okay, because yeah. So if you take, so I wrote the q in this way. Another person might write the q in the other way, right? So therefore, I wrote like this. Another person may create the q like this. Therefore, I will take this as answer 77778999. Right? So the answer is B. So that is question 4. Yeah, answer is B. So it takes time, but it is not difficult question as long as you can just concentrate on the logic. Okay, right. So let's move on to the next one then. It's again something like that. Just they check whether you can concentrate and understand a little bit of a complicated logic. Again, they ask the content of the queue. Right? Content of the queue. So that I am not going to do because I already did something like that. Okay, so I don't want to waste my time. So you must be able to do that as long as you know what is how the stack works, how the queue works, what is push, what is NQ, what is DQ, what is pop. You must be able to do this. Okay, so I'm not going to do that. So the answer will be C. Okay, right. Sixth one. Consider the following linked list. Choose the correct code segment that can remove both B and C nodes. Right? So that means at the end, B must have been removed, right? C must have been removed. So you know that how to remove B and C together. Simply what you have to do is you have to make sure that A's link is connected to D. Then this will be automatically removed because it can't look at two nodes. So therefore this will also be removed, and this one will also be removed as right because when C is garbage collected, this will also be removed. So what you have to do is you have to make sure that A dot next is right. Still these links are there, therefore we can still use it. So we want to make sure that A dot next is A dot next, that is B dot next, that is C dot next, right? So that is A dot next dot next dot next, right? A dot next is this one, its next is this one, its next is this one. Yeah, so we have to say A dot next equal A dot next dot next dot next. Okay, so let's see whether we have an answer like that. Yeah, so the answer must be B. Answer must be B. Oh, there are two answers, B and D. So I didn't check all the answers. You have to check all the answers. Now let's see whether D is also correct. Right, so anyway, B is correct. I didn't check all the answers. You have to check because multiple answers are possible. Now let's see whether the D is also going to work. So it says A dot next equal. So I will just delete these things. Right, now let's see whether it's going to work. Uh, A dot next equal A dot next. So A dot next means this particular link, right? This particular link. So therefore this will be broken. A dot dot next means this is A dot next. This is A dot next. So that means this link is broken. It is created like this, right? It is created like this. Now this is also garbage collected because no one is looking at this B node. So therefore this will be garbage collected. Therefore this link will also be invalidated. Right, now there's another statement A dot next. Now A dot next is this guy because now this is garbage collected. A dot next is this guy, right? A dot next equal A dot next equal A dot next. Now A dot next is this guy. Its next is this guy now. Now remember, now this is not no longer there. A dot next is this guy C. Its next is D. Now it says A dot next. That means this link must be looking at this guy. So it can't look at both the link object. Therefore, this will be removed. This is removed means this is garbage collected because no longer no one is looking at that. This garbage collected means this reference variable is also not there. So now again you can see that we are creating a link from A to the this D node. Yeah. So therefore that is also correct. Okay. So that is also correct. So this kind of question you better check all five answers. I just look at only this one only. Yes, this is also correct, right? So it's first you link it from here to here, and the second statement link it from here to here, breaking this one as well. Okay, right?
Sir,
Yes,
sir,
yeah.
something went wrong. I can't see you. I can't see the board.
Anyone else having the same issue? Can anyone else see it?
Yes, sir, we can see.
Anyone else? Anyone else can't see? Can you just respond to the chat?
So we can see.
Others can see, right? Okay, so I think that person has a better you try to reconnect. Okay, so it looks like only you
Okay.
are having the issue. Okay, right, right. So then we will continue. Yeah, so we continue from that point. So you try to reconnect and see. Okay, so the answer is B and D. Now let's move on to the seventh question. Seventh question. Before calling pop in a stack, right, calling pop in a stack, what condition should be checked? We know that if you call a pop on an empty stack, we are in trouble. As long as your stack has data, you can pop. Okay, so that means you have to check whether your stack is empty or not. That is the only requirement you want to check, whether your stack is empty or not. If the stack is not empty, you can pop. But if it is empty, you can't pop because it will result in underflow error. Right, underflow error. Right. So now let's see the answers. Overflow, no, we don't have to check overflow, right? Underflow, yes, we have to check. Underflow has to be done, is going to happen. That means we have to check whether the stack is already empty. The maximum elements, no, you don't have to check the maximum elements when you are popping. Popping means you are taking out. No, existing elements. So we had to check whether there are existing elements, but that is not a very good answer because it says existing elements. We just have to check whether there are elements, not existing elements. Okay, so we'll not take that. Previously entered element. No, we don't have to look at that. Right. So the answer must be underflow. Right. So the answer must be underflow. But I think there's a small issue in this paper answer. Let's see the past papers answer. So yeah, it says B and C both, but I don't see why you have to check the maximum element. So I feel like that answer is wrong. Uh, but if you have any other opinion about that, just you can let me know in the chat or WhatsApp group or whatever. We can just talk. For me, only B is the answer. Okay, for me only B is the answer. It looks like C is a debatable answer. Okay, right. So but if you feel like C is also answer, uh, and if you see some sort of a logic, yes, you can just uh, say how do you feel about that. Okay, right. So let's move to the eighth question. Which of the following statements is are false? Right? Is are false. Arrays are static data structures, right? So when you create an array, usually, especially in Java, those are static. Those are not dynamic. If you create an array of size 10, that's all, right? So you can't create, increase it again. So then you have to create another array and copy all the elements to that array, right? Say if you want to make it 20, now you create another array of size 20 and copy those things here. Okay. Especially in Java, arrays are not global, right? So therefore that is correct, that is correct. Okay, second one, data elements in linked list do not need to be stored in adjacent space in memory, right? In linked list every node is linked to another node, so just the reference variable means it is pointing into the memory address of the next object. So they are not necessarily in adjacent places. They can be anywhere in your memory, they can be anywhere in your memory because it's just a pointer or reference variable, right? So therefore yes, but in a memory sorry, but in an array usually they allocate consecutive memory for arrays. But for linked list, there is no such requirement, right? So of course, these things are handled by your operating system and the JVM if it is Java. But in linked list, there is no such requirement. But for arrays, usually, typically, the memory is allocated consecutive. Memory locations will be given. Okay. So memory used in array and the data elements in linked list do not need to be stored in adjacent space in memory. Yes, right. So there is no such requirement. C. Memory used in an array and linked list to store any given number of values are the same. So it says memory required for arrays and linked list are the same. So usually arrays take less memory because it doesn't have to point to another memory location. It just can keep your data, right? It just can keep your data. Therefore, arrays take less memory than linked list. But in linked list, you have to keep the data as well as you have to keep the memory location of the next node, right? Keep the data, keep the memory location of the next node. There is no such requirement when it comes to array because always typically it will be using the next memory location for the next index. So therefore, yes, memory used in array and linked list to store any given number of values are the same. No, for me, they are different. Typically, linked list take little bit more memory than arrays. Okay, right. So D. Linked lists are collections of nodes that contain the information part and a reference to the next node. Yes, that is exactly what happens. So you have a data part, information part, and reference to or link to the next node. So that is correct. Right? E. Only arrays can be used to implement stacks. No, we can implement stack using arrays as well as linked list. Right? So we did both the implementation in the class. Yes. So therefore that is wrong. Only arrays, no, we can even use linked list to implement a stack. So therefore answer must be but the must be false ones. We'll go for C and E. Okay, C and E for 8. Yeah, C and E. C and E. Okay. Right. So if you have any questions, you can ask. 9. Consider the following program: public static long ABC. Now you can see there's a recursive call there. So this is method is ABC. It is recursively calling ABC. It looks like it is trying to calculate the factorial value because n into n minus 1. What would be the final return value of the above program? Right. So let's do a dry run. So it is going to send 5 here. Right, 5. Initially it is going to get 5. Now what if it is not 1, right? So therefore it is going to return n into now it is going to send 4. Next time it is going to send 3. Next time it is going to send 2. Next time it is going to send 1. So when you send 1, it is going to return as 1, right? 1. Then this is n into, that means 2 into 1, then that into 3, that into 4, that into 5, etc. That means it's factorial. Okay. So what is factorial of 5? 5 into 4 into 3 into 2 into 1. That is 5 into 4 is 20, 20 into 3 is 60, 60 into 2 is 120. So answer must be E. 9. Answer must be E. Yes, answer is E. Right, so let's move on to the 10th question. So at any time you can just raise your questions, okay? 10. Consider the following pseudocode algorithm which can be used to find GCD, right? So greatest common divisors, you have learned those things in your semester 1 introductory maths, GCD, of two numbers using Euclid's algorithm. So actually Euclid algorithm is in your the new syllabus, semester 1 math syllabus as well, because they have modular arithmetic in your semester 1 maths. So Euclidean algorithm is a algorithm that we can use to find the GCD of a two numbers, greatest common divisor of a two numbers. So GCD means something like if you have 5 and 20, right? So the GCD is 5. Right? If you have 12 and 18, the GCD, greatest common divisor, is 6, right? So you know what is mean by GCD, right? Right. So anyway, forget about the algorithm because they have given you the logic, right? If one does a dry run of the above pseudocode algorithm, what would be the return value? So you can just actually you can do two things, since assuming that this person has implemented this properly. If you know the GCD of 54 and 6, right, you can just write down taking a small risk, right? So what is the GCD of 54 and 6? 54, is it divisible by 6? 54, is it divisible by 6? No, no, right? Then is it divisible by 3? 3, no, right? It's not divisible by. Anyway, let's do this. It looks like the GCD is going to be 1 then, okay? Because 54 is not divisible by 6. It is not divisible by. It is divisible by 2, right? Both are divisible by 2, so it looks like answer is going to be 2. Okay. Anyway, let's do a dry run. And it looks like answer is going to be 2 because it looks like the GCD of these two are 2. But anyway, let's do a dry run. So 50 A will be A will be 54 initially, 54, and B will be 6. Right? Right now, if B equals 0, return A. Now B is not equal 0, therefore it is going to call again that same method, right? With A B, it is going to now B A. Now the value of B becomes your A. Now you can see B is becoming your A now. Therefore now A is 6. And your B is, that is your second parameter, is going to be A mod B. A mod B is A is still 54. 54 mod 6 means if you divide 54 by 6, how much you get? 9 into 6 is 9 into 6 is 54, right? Yeah. So that means actually the answer is going to be then 6 because there are 9 sixes for 54. So it looks like answer is going to be 6. Anyway, let's do this, right? So 54 mod 6 is 0, right? Because A mod B, A is 54, B is 6, 54 mod 6 is going to be 0, right? 0. Now it is again going to call this with A equals 6 and B equals 0. Now you can see that now this time B equals 0. B equals 0 means it is going to return A. It is going to return A. So the return value of A means it is going to return 6. Now it is returning 6. Right? It is returning 6. And again it will be returned. Right? So the final return will be 6. So the answer is 6. So that is what we guess also, because GCD of 54 and 6 must be 6. Okay. Right, now let's see the answer. Yeah, answer is 6D. Okay. So anyway, I will again explain if you don't get it. Right. So now remember, now this is initially A is 54. Right. A is 54. B is going to be 6. Right. So this is going to be called with A equal 54 and B equal 6. Now here what happens is if b equals 0, it is going to return a, but it is not 0, therefore it goes to the else part. It is again calling itself, so that means it is calling itself. Now you can see that your first parameter is b now. Now earlier your second parameter is b, now the first parameter will have the value of the b, therefore your first parameter is called a will be 6, and the second parameter is the b parameter, so that is going to have current a mod b. Current a mod b is 54 mod 6 is 0, right? So now when it is called with these two values, now the b is 0. When b is 0, it says return a, therefore now this is going to return 6 because it has written a, right? Now this guy has to also return that value because it is keep on returning, right? Keep on returning, or actually there is no more return value. That is a final outcome because there is no, it's not, it never went to more than one step, therefore the final answer is 6. Okay, final answer is 6. You can do this for some other, because this is a very famous example algorithm. Even your new syllabus students have this algorithm in their semester 1 as well. So this is another use of recursion, right? Another use of recursion find in the GCD. I think this question has been asked in your second paper as well, in some years, how to find the GCD using recursion, and also we can find the GCD using stack also, right? Stack also. So therefore you better note this one, and also do a dry run for this algorithm using something like say 24 and 18. So then you must get the answer as again 6, right? So do a dry run and see whether you are getting 6, or do a dry run for something like 30 and 27, so then you must get something like 3. Okay, so right, so it's up to you to do a small try run, and actually it's better to remember this algorithm as well in case they ask it in the second paper. Okay, right. Question 11. Suppose a binary tree is constructed with n nodes such that each node has exactly either 0 or 2 children. Right? So that means it's something like this. So this is valid. This is valid. Then next one must be this one. So this is not valid because this guy has only one children. So the next valid one is this one. Okay. So what is the next valid one? This is not valid because this guy has only one, because it says exactly 0 or 2 children. So this is invalid. So it has to be something like this, or it can be something like this. That is also valid because here 2, here none, here 2, here no children, no children, right? So what is the next level it can go? It can go something like this as well. Now you have to see whether you can see the pattern, something like this. So that is also valid. Okay, that is also valid. Another one will be something like this. Something like this. Or those two can be here, those two can be here, or combination likewise. Okay, right. Now let's see what is the question. Suppose a binary tree is constructed with n nodes. Now here n is 3, here n is 1, n is 3. Here, right. So here n is 1, here n is 3, here n is 1, 2, 3, 4, 5. Right. Here n is 1, 2, 3, 4, 5. Right. This one 1, 2, 3, 4, 5, 6, 7. And this one is also 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, so likewise. Okay, right. The maximum height of the tree will be, right. So now you have to check using this n, what is the maximum height. For example, when n equal 1, height is 0, right? Height is 0. So when n equal 1, height is 0. When n equal 3, because you can't have n equal 2, the height is 1, right? 1. when n equal 5, the height is 2. Right? So this one. This one also 5. Again the height is 2. Right? 1, 2. Right? When n equals 7, because you can't have n equals 6. When n equals 7, no, this is 1, 2, 3, 4, 5, 6, 7. Yeah, 1, 2, 3, 4, 5. That is 2. Here also it is, yeah, there also it is 2. Right? There also it is 2. Then when n equal 9, your height is 1, 2, 3. 1, 2, 3. Right? So that what they ask is maximum height. So that means when n equal 5, maximum height is 2. When n equals 7, the maximum height, no, when n equals 7, you can go for something like this also, right? For this one, this, 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 right? So that is also possible. Right? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. So what we need is a maximum height, okay, not the normal height. So if we want to go for maximum height, we have to make sure that it is growing at one end. Okay, so I'm going to draw it again now. I didn't see this maximum height concept. So then it has to be something like this. So this is only 1. This is 2. If you want to get it to the maximum height, let it grow like this. Grow like this. One side only. Next one, grow like this, one side only, grow like this. Now you can go for the maximum height rather than having this somewhere here. So if you want to go for another level, grow like this. Now I am not violating the concept. So each node has either 2 children or no children, and I want to go to the maximum height also, something like this. Or it could have been connected to here also, right? But it must be something like this. Now let's see. When nodes is 1, maximum height is 0. When nodes are 3, maximum height is 1. When we have 1, 2, 3, 4, 5, the maximum height you can go is 2 because you can't create more than this height. Then 1, 2, 3, 4, 5, 6, 7, the maximum height is 1, 2, 3. When we have 1, 2, 3, 4, 5, 6, 7, 8, 9, the maximum height is 1, 2, 3, 4. Now let's see whether we can find a pattern using these things. Okay, right. So 2n, so n is number of nodes, this is height. No, 2n is not going to work. No, because it's then height is going to be 10 when we have 5 nodes. No, n squared minus 1, no. For example, 3 squared is 9, 9 squared 9 minus 1 is not 1. N minus 1 divided by 2. So for 3, 3 minus 1 is 2, 2 divided by 2 is 1, correct. For 5, 5 minus 1 is 4, 4 divided by 2 is 2, correct. For 7, 7 minus 1 is 6, 6 divided by 2 is 3, correct. For 9, 9 minus 1 is 8, 8 divided by 2 is 4. It looks like this is correct. If you are in doubt, you better try it for another one, right? So it looks like this is correct, right? Let's look at this one also. No, it's not going to work because the 2n plus 1 means it's going to be bigger than the number of nodes. So here n log n plus 1. So let's look at that one also. When assume that this is log 2 usually for this kind of questions. When n equal 3, 3 plus 1 is 4, log 2 4 is 2. Uh, so 3 into 2 is 6. No, it must be 1. So that is also wrong. Right? So therefore it looks like this C is going to work. C is going to work. Now remember why I am drawing like this, because it says maximum height. So therefore I am trying to make it long and long and longer. Right? Long and long and longer, because I could have drawn something like this, but then I am not going for the maximum height. So therefore I want to fix it somewhere here or somewhere here. That is also okay. but each time I want to go into a next level, right? Next level, right? Okay, so let's see the answer. Answer is C, correct. Answer is C. Okay, right. So let's move on to the 12. Consider the following binary search tree. Suggest a suitable nodes as the replacing nodes if one wants to delete the node with the key value 8 from the above binary search tree. So you know that when you want to delete a data from a binary search tree, there are three scenarios. That node has no children, that node has one children or one child, that node has two children, right? So let's see what kind of scenario is this one. uh, so so it won't delete 8, so 8 is this one, 8 is this one, so that means not having two children, right? Two children. So what we are supposed to do when we are deleting not having two children, we have to find the in order successor and replace with that. That's it, right? So how to find the in order successor? There are two approaches. Go one left and keep going right until the leaf, or you go one right and keep going left until you find a leaf. Okay, so now let's see, let's do for the go one left. So go one left and you have to keep going down right. So that is 7. So 7 is a candidate. 7 is a candidate. So let's that means I can replace 8 with 7. Right? 8 with 7. Now you can see it is not, it is preserving the binary search tree property. 3 is less, right? 6 is bigger. 6 is no longer there. Yes, so that is okay. Right? So what is the other approach? Go one right and keep moving left, right? Go one right and keep moving left. There is no ways to go left, therefore it is going to be 10. It is going to be 10. So the 10 is also going to be a candidate. Okay, so let's see whether if we put 10 here, is it going to work? Yes, 14 is bigger, 13 is less. Yes, it's going to preserve the binary search tree property. So the answer must be 7 and 7 or 10. So that is B E. 12. Yeah, BE. Okay, BE. Right, 13. Consider the following incomplete sentence. Right, let's take one by one. A with no duplicate elements has a property that for every node in the tree, the value of any node in the left subtree is less than the value of the node in the value of the any node in its right subtree is greater than the value of the node. So that means has the property that for every node in the tree, right? For every node in the tree, the value of any node in its left subtree is less than the value. That means what? Binary search tree. So that means sorted somewhere like here, right? So that means all the time, all the values left side is less than this guy, all the values right hand side are greater than this guy, right? So that is exactly what we found in the previous examples as well, right? For example, this is a that kind of a thing, right? So for example, if you take 8, all the guys in the left side are smaller, all the guys in the right side are bigger. Okay, so if you take another one like 10, all the people in the left side are smaller than 10, all the things in the right side are bigger than 10, right? So that is exactly the definition of binary search tree. Right, now let's see. Right, binary tree. So what are the answers? Binary tree, yes, that is exactly what it means by that. Binary heap, no. Binary heaps are sorted either top to bottom or bottom to top. There is no such requirement for sort like this way. No. AVL tree, yes. Why? AVL tree is also a binary search tree. It's a balanced binary search tree. So therefore, AVL tree is going to naturally fulfill this. So therefore, this definition is going to work for AVL trees as well. But AVL trees fulfill not only this particular definition. It is going to fulfill another property, that is, for any node, the balance factor is going to be less than 2. Okay, so that means it's going to be 0 minus, so not less than 2. The balance factor is going to be 0 minus 1 or plus 1. But still, it's a tree, search tree. Therefore, we'll take that. Binary heap. No, I don't know why the same answer is twice. Right. So he also binary heap. He also binary heap. So anyway, it's not good. Binary search tree. Okay, so I made a mistake. So here it says only binary tree. So actually the answer should have been what? Binary search tree. Binary tree means there is no sorting mode. Actually this is wrong, right? So the answer must be binary search tree and AVL tree, because this is just a binary tree. So in binary tree we don't expect any sorting. Okay, so answer must be C and E. C and E. Let's see. 13. C and E. Right, so let's move to the 14th. Consider the following figure. The above figure 1 shows table of contents of a book using a tree representation. Which of the following statements these are valid in connection with the above tree? Right, so that is not a difficult thing. Just check whether you know the terminology. First, A. Book is said to be parent of. Right, so let's make it a little bit smaller. Right. Book is said to be parent of C1, C2, C3. Yes, C1, C2, C3, correct. C1, C2, C3, yeah, book is a parent. And C1, C2, C3 are said to be children. Yeah, C1, C2, C3 are children of, let's say it's book. Yes, so A is correct. A is correct. What about second one? C1, C2, C3 books are siblings. C1, C2, C3 are siblings. Yes, same level. Right, so they are siblings. Yes. A correct, B correct. Because same parent, C1, C2, C3 have the same parent. Height of the tree is 2. No, height of the tree is the maximum height of the any node. So here the maximum height is 1, 2, 3. Right? So 3 levels are there. 1, 2, 3. No. The ancestors of S2.1 are node itself, C2 and book. So ancestor of S2.1. So what is S2.1? So S2.1 is this guy. Okay. So its ancestors are C2, yes, node itself, C2 and book. So can we take that node itself as ancestor? So usually ancestors means the previous guys, right? So I don't like this node itself part, but I am not sure why the examiner has added that as answer. I will say no, right? So because of this node itself, right? I don't know whether node itself can be considered as an ancestor. I will say no. Okay, right? So E, length of the path from book to S2.1.1 is 4. So what is S2.1. S2.1.1 is this one, starting from book to, yeah, book is here. So the length is 1, 2, 3. Right? 1, 2, 3. That is not level, that is length. Actually, it's less than the level. Okay. So it is not 4, it is 3. Right? So I will not go for that. So in that case, for answer is A and B. Right? A and B. Now let's see the answers. Oh, different answer. Why is that? They have taken A. That is strange. Why B is not taken? Can you see why B is not an answer? A correct, okay. C1, C2, C3. C1, C2, C3. Sorry, and book. So sorry, I didn't see that. C1, C2, C3 and book are siblings. No. C1, C2, C3 are siblings, but book is not a sibling. So I didn't see that. Okay, sorry. So yeah, B is not an answer. Now why they are taking D as answer? The ancestors of S2.1 are, so that means they have taken itself also as ancestor. So I'm not very sure about that, but maybe that is the case. It looks like they consider itself for note itself also as ancestor. So you better note it down for your exam. So when we say ancestors of this particular node, that means itself, this, and this. Okay, so so itself also has taken as ancestor. Okay, right. So that way you better note it down. Okay, because in the exams they may ask this again. Right. 15. How would you construct an AVL tree when a set of numbers is given without performing any single or double rotation? Right. So that is an interesting question. Now we know that when we are creating AVL tree, when it is imbalanced, sometimes you have to do single rotation. That is something like left, 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 or right, right, right. You have to do single rotation. If it is left, right, or right, left, you have to do double rotation, because first you have to rotate to get it right, right, and make it balance. Or here also you have to do double rotation. So what they ask is, how would you construct an AVL tree when a set of numbers is given without performing any single or double rotation? So that means when you are creating the your AVL tree, you must be able to create it without doing any rotations, right? So that means it must be naturally balanced, right? So that means you must have your data in a very symmetric manner, right? Symmetric manner. Then you don't have to do any rotations, because it will be naturally something like this, something like this. It is going to fill in a very natural way, right? Very natural way. Uh, I think still it's okay. Yeah, if it is feeling like this, not necessarily like this, after these two, even these two can be filled, but still it is balanced, but it has to be very symmetric way. You can't feel like this. No, then it is going to be imbalance somewhere here. Okay, right. Now let's see the answers. I think this question has been repeated. uh, just build the tree with the given input as the way of constructing VST, that is binary search tree, without considering the balance factor. No, if you are not considering the balance factor, or if you are just inserting, after sometimes there is a possibility of it is getting imbalanced. So that is why we have the rotations, right? So let's not take that. Use trial and error methodology. No, that's not going to work, right? So if you just use trial and error or whatever, it's not going to make it balance all the time. After sometimes it will be unbalanced. Find the median of the set of elements given, take it as a root or parent, and construct the AVL tree. Actually, that is the answer. I think you better note it down, because these kind of things you have to remember actually. So if you have a set of data, so if you are talking about the median, it must be sorted also. So they have not mentioned that. So you have to note it down as data must be sorted, and you have to start with the median, right? So I will give you an example. Say something like this: 5, say 10, 20, 25, 50, 80. How many data? 1, 2, 3. Let's add one more data, 100. Now this is sorted, and the median is 25. Now if you start from the median and keep entering data like this, 25. Then again you have to go to the median of your left subtree and the right subtree. In this case there is no the one value, therefore you can go for anything, either 10 or 20. I will go for 10. Then 5. Then right side also you have to do the same. Either you have to go 50 or 80. I will go for 50. Then here now 10 is also done. 80 is also done. Now you have to go for 5. and of course you can go for 20 as well. Still it is not balanced, unbalanced. Then here you have to go for say, sorry, this is 80. You have to go for 50 and 100. Now you can see if you have so many data also, still it is going to be really balanced all the time, because you are just going for only one level, then again you are going for the next level, etc. It's always going to be balanced, right? So what you are supposed to do, you better remember that, make sure your data is sorted, and you have to start with the median, that means the middle part. You have to do that for each and every half. Again go to the median, again go to the median. Right, so okay, then it is going to be always balanced. Okay. Uh, so D is anyway wrong. Those are wrong answers. So the answer must be C. Right, so that you better note it down. If you want to make sure that your ABL tree is always balanced without doing any rotations, make sure you sort it and keep inserting the median of the each sub portion, right, starting from the big median. Okay. Yeah. Answer must be C. Answer must be C, right? So that is actually something you have to note it down. Uh, right, 16. Consider the following pseudocode algorithm. Uh, what is the above pseudocode segment intended to do? Now let's see what it's trying to do. So this is also a very famous question. Anyway, this question has been repeated over and over and over. So what it does is, now you can see that it is starting from this ABC method is given a node, right? So if it is null, it is returning 0. If not, it is returning 1 plus taking the maximum, right? Taking the maximum of the left subtree and right subtree. Again, it is calling recursively, right? Recursively calling. So at the return type, return trip, it will take the maximum of those two values and add to that particular one, right? Uh, and add one to that particular one. So it's going to keep doing like that. So what will happen is, if you do this kind of algorithm, so that is a very famous algorithm, it will give you the maximum or the height of your tree. Uh, so if it is something like this, it's not, it's for any binary tree actually. Say it's something like this. So first it will be calling for this one, then because it is not null, it is going to call it the same method for its left subtree and right subtree. That means for this node and this node. But when you are recursive calling, you have one plus and calling itself. Then for this one, it is calling itself using these two. For this guy, it is calling using these two. Then for this guy, it is going to be null, right? Left and right is going to be null. They are going to return as 0. Right, so here also there's a left guy, then again here it will be 0, here it will give you a value, therefore the maximum will be 1. Likewise, every time you go into a level, one value, it will be incremented by 1. So ultimately, since you are taking the maximum value of your left and right, it will give you the maximum height. For example, in this case, 1 2 3 4, right? So likewise, uh, so you better run this code and see whether you get that maximum height, right? Maximum height. Remember, we implemented a few of those algorithms: how to insert data, how to search data, right? How to find the minimum, how to find maximum. For that code, so the code is available in the code link in the site, right, for the trees. So you can implement this one as well and see whether you are getting the height. Definitely you must get the height. Okay, definitely you must get the height. So that is a very famous algorithm, finding the height, right? So right, it's going to give you the height, not the length, right? It's going to give you the height. So that is why we are taking the maximum of your left subtree and the right subtree again. So the answer must be C, right? Answer must be C. Answer is C. Okay. And if you're not clear, just let me know. I can again explain it, right? You can, I have uploaded the code. You can just get the code and again write this code, this method also there, and run it and see whether you are getting the correct answer. Okay. 17. Which of the following are not applications of the breadth first traversal algorithm? Right. So we did the breadth first traversal for graph. For the trees, actually I forget to mention in the class, for the trees, breadth first traversal means pre-order traversing. Because in pre-order traversing, we go, remember we have, for the trees, we have pre-order, in order, and post order. So in pre-order, it is root left right, root left right, in order left root right, right. Here it is left right root. So root is the this guy. Right. So now you can see here we go to the pre-order. We first, sorry, root is this guy. First we go to the root, then left right. So that means we try to stay closer to the root. Stay closer to the root. So that is what is mean by breadth first traversing, right? So the depth first traversing is pretty much like a left right root, because you try to go into the depth, right? So similarly we discuss it for the graph as well. So in the graph we anyway discuss it as a two traversing methods, the breadth first and the depth first. Okay, right. Now let's look at it, the answers. What they ask is not applications of breadth first traversal, right? Not applications. They have not mentioned whether it's a tree or graph, but it looks like they are talking about a graph, not a tree. Right. When finding the shortest path of a unweighted graph. So it looks like graph. Now remember, breadth first traversing is something like this. Where you go this guy, then this guy, then this guy, then you go to this place, because that is from here you have to go. So this is yeah, breadth first, then you go to this, right? Then if you have another one, then you go to this one, right? So is it going to work with the shortest path of unweighted graph? I don't think so, right? So shortest path and breadth first traversing, I am not sure. According to my mind, it has no connection. Okay. When assigning processors to CPU in a round robin fashion. Now remember, breadth first traversing has something to do with the, remember, queue. The depth first traversing has something to do with the stack, because we try to go further and further away, right? But here we try to stay closer, then next level. So you can see it's sort of round robin. So these guys have given the first visiting, then these visiting, then next level, then next level. It looks like there's a small connection between that, because there also we have to give first priority to these guys, then its subprocessors, its subprocessors, etc. Uh, so we'll take it as it is. Peer-to-peer networks. So peer-to-peer networks means networks where any node can communicate with any other nodes, right? Peer-to-peer. I don't know whether it has any connection with the breadth first traversal. Right? Breadth first traversal is a very special one, right? So I don't know. When evaluating a mathematical expression, so when we are evaluating mathematical expressions, we use the stack we used, and also we use the binary search trees to represent it in order, uh, infix notation, and then converted it to prefix or the postfix. So therefore, I don't see it has a connection with the breadth first traversal, but it has a connection with the binary search trees, stacks, etc. Right? So I will not take it. GPS navigation system. Of course, GPS navigation system is part of your is a usage of a graph, but I don't see it has something to do with the breadth first traversal, right? Because breadth first traversal and Normal GPS navigation, because in normal GPS navigation we just navigate, right, towards our destination, or maybe we like to see the shortest path or something, right? So I don't know. It looks like no. It looks like no. So the only doubt is B. Now let's see what is the answer is. Okay, so what they ask is not once. Yeah, so the not once, not the correct ones. So this is actually the right one I thought, but they asking is not one. So but what happens is they have not. They say now A is okay, C and E. C is okay, E is okay. That means they think that D is also not application. Sorry, D is not D is a application. I don't know how the mathematical expression evaluation and the breadth first traversal has any connection. So you better do a small Google search and see whether is there a connection between evaluation of mathematical expressions and breadth first traversing. Right. So I can't remember. What I can remember is it has connection with the stack. Obviously, once it is converted to postfix, we use a stack, and also we can use a binary tree to represent it in a infix notation, and then we can do a post order traversing to get it as a postfix notation. Okay, so you better check whether what they mean by this. Okay, how this is going to connected with the first breadth first traversal. Okay, so that is a sort of a something you have to do a small research. Okay, right. So let's move on to the 18. For a given graph G having V vertices, E edges which are connected and no cycles. Now remember, if they when they say it's a graph, and at the same time when they say no cycles, so graph having no cycle is a binary tree. Actually not a binary tree, it's a tree. Right? So graph having no cycles means it's a tree. Right? It's a tree. Right. Which of the following statement these are true? So that means they are talking about a tree, right? Not though they call it graph, because no cycles means it must be a tree. Okay, right. Now let's see. V equal to E plus 1. V equal to E plus 1. Now let's draw a tree, something like this. So this is an example of a tree. This is also an example of a tree, because it can have, because they are not talking about the binary tree. This is also an example of a tree, something like that. And this is also an example of a tree. Likewise, now we have to think about it, something like this. Maybe something like this is also a tree. Likewise, now it's a very complicated question. Then they ask v equal to e plus 1. So what is v is vertices. So vertices are nodes like this. E is edges. E is edges. Now you can see two edges. Now I'll take this one. Two edges, three vertices. Right? Three vertices. So this is vertices. This is edges. Okay. Now let's take this one. Four vertices, three edges. Now let's take this one. One, two, three, four. Four vertices again, three edges. Right? Three edges. Let's take this one. One, two, three, four, five, six, seven vertices. How many edges? One, two, three, four, five, six. Now it looks like when it is a binary tree, not only binary tree, for any tree, you can see that edges, number of edges is less than number of vertices. Now let's look at do it for another one, just to double check. Let's say one, So let's take it 4. Let's have this one having 3. Maybe this one having only 1. This one having only 2. Now let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 vertices. How many edges? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, it's always less than 1. So you better remember that as a property as well. So whenever there's a tree, so that is why we are doing a lot of past paper questions. When it is a tree, your number of edges is always less than number of vertices. It is true for any tree, not only for binary tree. Any tree that is going to hop, right? So anyway, they are talking no cycles, therefore it must be a tree. So therefore we can take it as E equal v minus 1, because E equal v minus 1. E equal v minus 1. So we can go for this one, right? So then is this going to work? V equal 2e plus 1. No, right? So v equal to e plus 1 is 3. That is 2 into 2 is 4 plus. This should have been 5. No. V equal e plus 1. So that is also correct, right? So same thing, right? Either you can say e equal v minus 1 or you can say v equal e plus 1. So same thing. V equal e. No. V is e plus 1. So wrong. Sufficient facts are not available. No, we can derive, right? So we can see that always number of edges is less than number of vertices as long as it's a tree. So therefore need not take that also. So that means answer is B and D. B and D. Now let's see the answer. 18. Yeah, so they have given only B, but if B is an answer, obviously D must also be an answer, right? Because if V equal E plus 1, we can say E equal V minus 1. So I don't know why they have taken only B as answer. I think it's a mistake in the answer sheet. So if B is an answer, D is also an answer. Okay. So if you feel like D is not an answer, just let me know your thoughts. Right? Can it be that kind of situation? No, I don't think. I don't think. Okay. So therefore, I will take both B and D as answers. Okay. Both B and D as answers. Right. So let's move to another question. The number of elements in the adjacency matrix of a graph having n vertices is, right? So that is again something we have to look at it. The number of elements in the adjacency matrix of a graph. Now remember, right? So adjacency matrix, right? Yeah. So if you have a graph, now let's take this one as example. Now this one, forget about the direction for the time being. I'm just taking this one as example. Right? How to draw the adjacency matrix? For A, B and D are adjacent. B and D are adjacent. So how to draw that? As a matrix, remember? So if you have 1, 2, 3, 4, 5, you have 5 elements, 5 by 5 matrix. 5 by 5 matrix. 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. For example, if you take A as the zeroth one, there's A to B. Right? A to B means here it is 1. A to D, say A, B, C, D, E. A, B, C, D, E. Right? So there's A to B, and also there's A to D, A to D. So others are 0. Then from B to A and B to C, others are 0. C to B and C to E, others are 0. So likewise, what is the size of the matrix? If you have n nodes, you are going to get n by n matrix, right? N by n matrix, right? The number of elements in the adjacency matrix of a graph having n vertices is. So now this is n vertices. So these are the n vertices nodes. If you have n vertices, we are going to have n by n matrix, right? N by n matrix. Therefore, the number of elements are going to be n squared. N squared, right? So the answer must be C. Answer must be C. Right? 19. Yes, answer is C. Right? So that's you can just memorize it that also. If you have n number of vertices, you are going to have n by n matrix because you have to find out all the possible direct connections, right? Direct connections or direct edges. 20. Consider the following graph. What would be the depth first traversal of the above graph? Now remember this is depth first traversal. Look at the answers first. It looks like they have started from A. Therefore, let's start from A. Right. So when you have a two more than one possibility, we always go for alphabetical order. Right. So therefore, from A, now this directed one. Therefore, I will go by the direction A. I will go for B. It is depth first. Therefore, I try to go as much as possible because that is not breadth. From B, I can go to C or E. I will go for C. Right? So that is one possibility. Then from C, I will go for E. Now I can't go anywhere else because then I have to come back here. Then I have to come back into B. Then I no point going to E again because I have already visited E. Therefore, I can go back to A. From there, I can visit D. Again, no point going E because already I have visited. Therefore, I am coming back to A. Then from A, I don't have any place to go. That means I am done. So A, B, C, D is an answer. Right? So E is an answer. A is an answer. Right? If you take it as a chronological or the alphabetical order, right? So usually they expect it to be alphabetical order, right? Alphabetical order. So therefore answer is A, B, C, E, D, right? A, B, C, E, D. So let's see the answer. 20. Oh, so many answers are there. C is also answer, but they have taken A and E also as answers. Now let's see why. A and E also they have taken as answers. Now let's see why. A and C. Right. So what is A? A, B, E, D, C. Now let's see whether it's going to work. A, B. Now let's see whether it's possible. Start with A. Yes, A from A to B. Correct. Then they have rather than visiting C, it has visited D. Right. So usually we go by the alphabetical order, but if that is not a hard and fast rule, so that is actually that's something you have to remember. Yes, usually we go for the next alphabetical level when you have E and C, but that is not a hard and fast rule because E is also one away from B, C is also one away from E. Therefore, someone will say, okay, so rather than visiting C, I will be visiting E. Therefore, we have to take that also as answer. A, B, E. From E, you can't go anywhere. You have to come back. Then you have to go to. So that is wrong then. From A, B, if you go to E, then you have to go to C. So that means B is not answer. Actually, that is. I think that is why I have made it yellow. That is not answer because if you go from A to B, yes, you can go either C or E. But if you go to E, now you can't go to D from there. You have to come back to B, and now you have to go to C, right? Then of course you can come back and go to D. So that is not answer, right? So I think that is a mistake in the answer sheet. Okay. So if you feel like it is not a mistake, you can just always challenge it, and you can share your thought. Okay. Right. So but now let's see whether C is an answer. let's see the C is an answer. A, now it is going D, of course, because it is also one away. Rather than going for B, you can go for D. From D, you have to go to E now. Yes, A, D, E. From E, you can't go anywhere because there are no arrows outwards. Therefore, you have to come back to D, not nowhere to go. Come back to A, then you can go B, right? Then there you can go to C. Then you will come back, nowhere to go, come back, nowhere to go, you are done. Right. So E and C are answers. Actually, I took only E because I went by the alphabetical order only, but don't consider it as a hard and fast rule. You can go by any order, right? So therefore, this is correct, but it looks like this is a wrong answer, right? Though it's the marking answer sheet says like that. Okay, right. So let's move to the 21. Assume that you have a directed graph representing all the flights that an airline flies. What algorithms might be used to find the possible sequences of connections from one city to another? So it's sort of it says graph, right? So it's already says graph, what they're asking. Assume that you have directed graph, right? So directed graph, so that is something like this. Something like this. Representing all the flights that an airline flies. So there can be flight from here to here, there can be flight from here to through here and then going there, and likewise. Okay. What algorithm might be used to find the possible sequence of connections? So that means all the possible sequence of connections from one city to another. So that means whether we can start from one place and reach to another place, right? So can I start from one place and can I go to this place from here? Now we can say obviously no, right? You can't go from here to here, right? But you can go from maybe here to here through this path. Okay. Now it says which algorithm is going to find those possibilities. So of course the breadth-first and depth-first traversal is going to work because when you are starting from one particular place, your breadth-first or depth-first traversal is going to go through all the possible places, right? For example, here from here to here, if say it's a depth-first, from here to here, then you are coming back and say okay from here to here, from there to there, from there to there. Now you can see all the possible places you found, right? All the possible things. Uh, so depth first also is going to work. So right, breadth first also going to work. So the pre-order traversal means basically the breadth first. Okay, pre-order means no, right? Pre-order. No, there is nothing called pre-order in binary trees. Sorry, graph. Pre-order is something to do with the binary trees. Right? So there, so will not take that. But breadth first and depth first is going to work because we are going to traverse each and every node, possible nodes. Right? Linked list traversal, I am not sure what is mean by linked list traversal. Shortest path algorithm, that I am not very sure. The shortest path is going to traverse. Are we going to check each and every path? I am not sure about that. I am not sure about this. But pre-order traversal is something to do with the binary trees, not to do with the link, the graph. But these two are going to work because they traverse each and every node possible. Okay, I will go for A and D. A, D, and they have taken E also. So that means they have taken shortest path algorithm also as an answer. Just double check with that. I am not very sure why whether it's possible. Maybe it may be some uh, some additional outcome. I'm not very sure about that, but anyway, A and D are going to work, okay, because we are going to traverse all the nodes, okay, right. So let's move on to 22. Right. So what is the time complexity in big O notation? Right. So that's an interesting question. So they have given you an algorithm. Now let's see whether what is the time complexity of this one. Now remember, if you have something like a loop, it's going to be n. If a loop goes from 1 to n. If you have loop of a loop, say this is n, assume this is also n or m or whatever, but something like in a loop, then it is going to be n squared algorithm, right? But if you have sort of a method like this, few statements only, we can just take it as 1, and we can just take it as 1. But if you have loop, it goes for about of course here also we can take it as n. For example, if you have n statements, we can take it as n, but it doesn't mean that it is going to depend on the data. Yeah, so this depends on the data. Yeah. Anyway, let's look at the answers. What is the time complexity of the following method? So you are sending array. If the array size is less than 100, return 0. That means if the array size is less than 100, the time complexity is going to be 1. Time complexity is going to be 1 because it is just returning. Only this line is going to be executed. Then what about if it is not less than 100? Now this is less than 100 because this is not going to be executed because it is written from here. Okay, returning from there. But let's see what happens if it is now. If, that means less than 100. If n is less than 100, time complexity is 1. What about if n is greater than 100? Because if it is greater than 100, it won't come to the if condition. It is going to the it is not coming to this if condition, but it is coming here. Then it says I equals 0 to 100, right? 0 to 100, you do that. Whether you are sending 1000 data of 1000 data or millions of data, still it is going to execute only for 100 times only, right? 100 times only, right? So 100 is sort of a magic number, fixed number. Therefore we can take it as maybe O1, right? O1, because 100 is a fixed number. You can't take it as ON. ON means it depends on the number of data. No, this logic does not depends on the number of data. Even when you send billions of data in an array, still this is going to be executed only 100 times. But if you are sending billions of data, if it is getting executed billions of times, we can say it's ON. But this is not ON, this is going to be definitely O1, right? Because it does not depends on your number of data. It's sort of a hard coded value 100, right? So rather than when we say 100 or 50 or whatever, we say O1, right? You can't say ON. ON can be used when only when your execution time is going to depend on the number of data. No, this is not the case. Your execution time is fixed one. It can be either 0, it can be 100. That's it. So therefore we have to say it's O1. Okay. So that is very interesting question. If you need any clarification, you can ask. Right. Right. So the answer must be B. Yes, answer is B. Right. 23. The following array is given. Bubble sort is used to sort the above array. How many iterations will be done to sort the array? Right. So it asks how many iterations will be done to sort the array. Now let's see. Now remember the bubble sort. So you start from the right 10. If you want to make it ascending order, you keep bubbling until you get the smallest one here. Right. Until you get the smallest one here. Then you start from again here. You keep bubbling until you get the next smallest here. Again you start from here, keep bubbling until you get the next smallest here, right? So next smallest here, next smallest here, next smallest here, you are done, because anyway this is going to be the bigger guy. So that means that is how it's going to work, right? So that means if you have 10 data, you are going to have 9 iterations, right? 9 iterations and so many bubble swapping. If you have 100 data, you are going to have 99 times you are going to iterate it, right? So because first iteration this will be sorted, second iteration this will be sorted, this will be sorted likewise. Okay, so here how many data is there? 1 2 3 4 5 6 7. That means you are going to have 6 iterations, right? 6 iterations, because seventh one you don't have to do, because anyway it will be now sorted, right? But for each iteration, we are going to have some mini iteration as well. Keep on starting from here, reaching here, starting from here, reaching here, starting from here, reaching here. Those are mini iterations, right? But the big iterations are 6. Okay, the number of big iterations are 6. I don't know whether they are asking about the small iterations as well, but if you go by the big iterations, the out iterations, it is 6. Right? And now let's see the answer. It's always one less than number of data. Answer is C, 6, because we have 7 data, it's 6. Right? So they have ignored the inner iterations. Okay. Right. 24. See the last question. No, two more questions. Following array of 9 elements is given to be sorted using quick sort. Right. So the quick sort we discussed in the class also. Actually, the biggest headache when it comes to quick sort is, of course, the general concept is the same, but there are so many tactics that you can use. Right. So many tactics you can use. So we discussed, I think, 2 tactics in the class. I saw one person has posted another tactic. I think that is a tactic most of the time your examiner is using. Therefore, I am going to explain that particular tactic. I'm not sure whether that is going to work for this question. For some questions, that tactic is working, right? So you can find that in the FB, not FB, the WhatsApp group. I answered to that one, that question, and mention that yes, that can be the most appropriate one. Anyway, so I will explain that tactic. You can find that in the WhatsApp group. So that tactic is, I think that is the tactic that this question has used. Anyway, are they talking about the pivot? Yeah, first element is the pivot, right? First element is the pivot. So I'm going to just copy paste this. I will explain that particular one again for others who have not understood it. The person who has posted it must know it. Uh, so let's do it here itself, because right, so I'm going to write this again, a little bit bigger. 54, 26, 93, 17, 77, 31, 44, 55, 20. Okay. Right. So this is my pivot. This is my pivot. Okay. So just listen carefully. Now the idea is, this is another quick sort approach. The idea is you are taking this one as your start, right? So that is one, or you can just start to consider this as 54 also, but no need. Say just one left of it as the starting point, and the final one as the end, right? Then what you are going to do is you are going to keep comparing this value with the pivot, right? So you have to keep moving rightwards until you find a value bigger than pivot. Right? So keep listen carefully. So you have to start from here and you have to keep moving leftwards, rightwards until you find a value bigger than pivot. So here it is the value is not bigger than pivot. So therefore you have to go again. 93, yes, 93 is a value bigger than pivot. Therefore I am going to stop at this point. Okay. Right. Now, this is my new start now. This is my new start. Now I am going to start from the right hand side. Now I am going to keep moving leftwards until I find a value smaller than pivot. Smaller than pivot. Okay. So in this case, this is my end. This end itself is smaller than pivot because 20 is smaller than 54. That means I don't have to travel right leftwards. I am already found a value like that. Right now that means my new start is here 93. My end is the 20. Right. So I can't move any further from left side. I can't move further from the right side. Therefore, these are the 2 points now I am in. Okay. Now what you are supposed to do is you are supposed to swap those two. Right. Right. Supposed to swap those two. Right. So let's again write it down. 54, 26, 20, 17, 77, 31, 44, 55 and 93 because we have swapped. Right? 20 came here, 93 came there. Now this is your pivot, still we are not done, and this is your new start. This is your new end or the old end because we were not able to move from there. Okay, right now again you have to do the same thing, starting from the current starts and end. Right, current start and end. Now again you have to check whether you have to move from start, you have to move rightwards until you find a value bigger than pivot. So still the pivot is 54. Now 17 is not bigger, 77 is bigger. Now that means this is not my start, this is my new start. Okay. Now you have to do the same thing from the right hand side again. Now again you still your right hand end is still the old end. Now you have to move right hand side, sorry left hand side until you find a value smaller than 54. Smaller than 54. 93 is bigger, I have to come. 55 is bigger. 44 is smaller, now I am done. So that means I came from 93 to 45 and this is my new end. This is my new end. Now again I found a start and end. Now I am again going to swap it. Again swap. Okay. So let's write it 54, 26, 20, 17, 77, sorry not 77 because we have to do the swapping. 17, 44, 31, 77, 55, 93. Still pivot is there. Now my start is at 44, my end is at 77 because we just swapped those things. Now again you have to do the same. Look at the start and end, and you have to keep moving right side from the start until you find a uh, value bigger than 54. Bigger than 54. Now 44 is not bigger. You have to come. 31 is not bigger. 71, 71, 70, sorry, 77 is bigger. That means your start is not here now. Now your start is here because now I found a value bigger than 54. Now you have to do the similar thing for the right hand side also. Now this is my end is still 77. Now I have to keep moving left side until you find a smaller guy than 54. 77 is not smaller. You have to go to 31. Yes, 31 is smaller. Therefore, this is my new end. right? So my start is now here, end is here. Now the start and end has crossed, right? So you have to stop when start and end has crossed. Now here, look at here, start is here, end is here. They have not crossed. Start is here, end is here, not cross. So that is why we keep doing. But now end is here, start is here. They have crossed. Right? When they cross, you have to stop. You have to stop, and now you have to swap your pivot with the end, not with the start, with the end. Now remember, now my start is 77, my end is 31. So therefore now I am supposed to swap 31 because that is my current end with the pivot. Then we are done. First iteration is done. Okay. So then the final answer is for the first iteration 31, 26, 20, 17, because now the swapping is between the pivot and the end, 44, 54, 77, 55, 93. And now pivot T is in the correct position. Now you can see all the elements left of the pivot T is less than 54, right of the pivot T is more than 54. So that is the idea behind quick sort anyway. Now let's see whether that answer is there. 31, 26, 20, 31, 26, 20, 17, 44, 54, 77, 55, 93. So that must be the answer. That must be the answer. The 24 answer must be C. Right, C. Right. But this is another technique. For some other questions, this technique is also not going to work. So that is a unfortunate behavior of quicksort. Different people can have different tactics, but this tactic work for this question, and also this tactic work for 2019 paper as well. And so therefore, you better remember this technique. You can find the YouTube video in the WhatsApp group, right? So I think about last week I saw that video. Okay, someone has published. So that is, it's a good thing actually. Otherwise, I have to spend some time to find out because there are so many variations of quick sorts. So now again this has to be done for this partition separately and this partition separately, taking 31 as the pivot and 77 as the pivot. So anyway, they have only asked for the first iteration, right? So the answer is C. Okay, right. So I hope you got it. If you are confused, uh, go through that tutorial, the YouTube video. So it explains a little bit in a lengthy way. So you must be able to understand that. Okay, right. Anyway, I will explain this again. There's another quick sort question, but for that quick sort question, this technique is not going to work. Okay, right. You can use this technique for 2019 question and see whether it's going to work. Actually, I published that into WhatsApp group as well. Right, answer. Okay, last week. Right. So that is 24. So let's look at the final question. There is an unsorted array of follows array as follows having 6 elements. The array needs to be sorted in ascending order. Heap sort is used to sort the array. Which of the following statements is are correct? Right. So there was a similar question in 2019 also. In the class, I told that I can't exactly remember how to do that. I will just do that again in the next class. So therefore, I'm going to explain it here. Okay. Right. So you know how to do the heap sort. So in heap sort, I think there's something wrong with the answer. Anyway, let's double check. In heap sort, what we are supposed to do is first we are supposed to make the heap. Then we want to take one by one out. Then we are getting the result as a ascending or descending order, right? So something what you have to remember is if you want to make it ascending order, make sure uh, you go for min heap, right? Min heap, sorry, go for max heap. If you want it descending order, go for min heap. go for main heap. Right. So here the question says you want it in ascending order, right? Ascending order. Therefore, you have to go for max heap. Ascending order means you have to go for max heap. Okay, you have to go for max heap. Now let's see how to do that. I posted about before starting the class. I posted a YouTube video, so that explains exactly how this is done, right? How this is done. So you can just again go through it, but I will explain it again. Anyway, I will just play that YouTube video. It's about only 3 minutes. I have the link. Yes. Right, so just I hope you can see the screen because I have shared the screen. You may not hear the sound, but you don't need sound actually. It's only music. You look at the both the heap and as well as the array. Right, so these are the data unsorted 4, 10, 3, 5 and 1. Right, so you can see it is not sorted. Now let's see how now this is the array. At the same time the heap will be also shown, but all those things are done in the array itself using the concept of heap. Okay, you know what is meant by heap? It is a binary tree sorted from top to bottom. Okay, right. So it will first create the heap. It is just adding the data. Right, now you can see this is the array. Now this array is represented by a binary tree, right? So they are just adding as it is 4, 10, 3, 5, 1. Now what it is going to do is it's going to make it a heap. So that means it will check from top to bottom whether the heap property is violated. Then it is going to do a swapping, right? For example, now you can see it's trying to make a max heap. Therefore 4 is smaller than 10. Therefore the 4 and 10 will be swapped. Okay, so something like that. 4 and 10 will be swapped. So when we say 4 and 10 is swapped, actually what is swapping is this array. So 10 will come here, 4 will go there, right? So then here 10 is there, here 4 is there. Okay, so then it will check again whether there is a violation. Now this 3 is fine, but here's violation, 5 is bigger, then these two are going to be swapped. So that means this 4 and 5 is going to be swapped. Right? So it's happening in the array using the concept of concept of heap. Then this will be 5, this will be 3, right? So then your heap is okay. Then it is going to remove this 10. So how to remove this 10? Now remember this is 5, this is 4 and this is 1. How to remove a data from a heap? It is going to be replaced by this last level rightmost element, right? So that means 10 and 1 is going to be swapped now. So therefore 1 will come here, 10 will go there. Then again it will check whether the heap property is violated. Obviously it is violated because now 1 is there. It is going to rearrange. But all those rearrangements will be done in the array, right? So I just gave you the brief explanation. Now closely look at this again and again. You can look at it because I have given you the video. Now closely look at what is going to happen. Okay. Now it's going to make the heap. Now it's fixing the heap property. Now the heap is okay. Now they are removing. Now again fixing the heap property. Now it is going to remove again 5 with 1. Now again fix in the heap. Now again removed. Now again removing. Right. So now you are done. So when you are done, your array is sorted now. 1, 3, 4, 5, 10. You can see. So using the concept of heap, those things are done in the array itself. But now the heap is now your array is sorted. Right. So that is very interesting thing. Right. So that is how it's done. Now let's see this question. I think this question has something wrong with the answer. Now you can see we went for the max heap. Why? The result is a ascending order. Right? Result is ascending order. If you go for min heap, the result will be descending order. Okay. So you can do it by yourself. Okay. Right. So now let's look at the past tense question. So let's put it into the heap first. So it will take a little bit of space. So make it heap first. So I will take some space from here. 4. So you need a lot of patience for this kind of questions and concentration. 4, 3, 7, 1, 8, 5. So just I am creating the array. Sorry. Just I am creating the binary tree. 7, 4, 7, 5. Right? 4, 3, 7, 1, 8, 5. I'm preserving the shape property. Right? That is why I'm going from left to right. And now I want to fix the make it a heap. Right? So there's a violation between 4 and 7 because 7 is bigger. So therefore 7 will go there. 3 will be there. 4 will come here. 1 and 8 will be there. And 5 will be there. Now this is okay. Now we have to check here. There's a violation. 8 is bigger, so you have to do a swap here. So that means 7, 8, 4, 1, 3, 5. Now this left hand side is okay. Right? No, still 8 is bigger. We must need to do another swap. Okay, another swap. That means 8, 7, 4, 1, 3, 5. Now left hand side is okay, but there's there's issue in right hand side. 5 is bigger, so you have to do another step. 8, 7, 4, 1, 3. Actually not 4. This would be 5, and this is 4. Now the heap is okay, right? Now we are going to remove the heap. How to remove the root? You have to replace it by the bottommost rightmost element. So that means 8 will be removed. Actually 8 will be replaced with 4. Okay. So therefore the new one will be 4, 7, 5, 1, 3. That's it. Because now 8 is removed. 8 is removed means now 8 is in the correct position, or the correct position in the array. Okay. I'm not drawing the array. You can draw the array as well. But for this question, we don't need the array. Okay. Right. Now we are done with that. And now again we have to fix the heap property. Now you can see 7 is bigger, therefore we have to fix it again. Right? So that means we have the 7 here, 4 here, 5, 1, 3. Now again done. Again it's a heap. Now we can remove 7 by replacing with 3. So then we will get 3, 5, 4, 1, 3. Right? So it takes a lot of time. Right? Then you have to remove 3, replace 5 with 3. Right? So likewise you have to keep doing. Then you have to check whether, now remember, if it is ascending order, you have to go for max heap. So therefore, these two are wrong. You have to go for max heap. Then you have to check whether any of these swapping has been done. For example, you can see there's a swapping here, there's a swapping here, there's a swapping here, there's a swapping here, right? There's a swapping here. Likewise, you have to check whether any of these swapping has been done, right? Any of these swapping has been done. So it's is it for the one step or the entire sorting? Yeah, so you have to go through few more steps here, maybe just 3 steps, and you are done. And check whether what kind of stepping is to which out of these which stepping you did it, right? You did it. Okay. So if you have any time, you can just do it by yourself and post it to the WhatsApp group and see whether answer is correct. Right? Answer is correct. Okay. So you have to keep doing this until you get it to this no your heap is empty, right? So that means just 3 more steps it will be empty. Then you have to check which swapping you did, right? So then you have to double check with your answer. Okay, just double check the answer and see whether the answer is correct, because I also didn't do all the things. But if you want, if you have any doubts, I can just hand do it, write it in a paper and post it to the WhatsApp group. Okay, so that is how we are supposed to do it. Here you don't have to look at the array, because they are just asking talking about the swapping. But when we say swapping, the reality is that is done in the array itself. Okay, but here you don't have to write the array, right? Right, so it will take a little bit time, right? So, but you must be able to do it. Okay, right. So that's it for the MCQs. So it's 10:10. Right, so what we are going to do is have to take more time here. Anyway, we'll do the second paper as well, because it won't take much time. Okay, it won't take much time. Right, so the first question: how will you implement a queue using 2 stacks? You may use a pseudocode or Java code to explain the answer. I think this question was there in 2019 paper. If I remember correct, I think yes. So how to use this 2 stack to implement a queue? Say you have one stack, another stack. So there are 2 ways. One approach is when you are doing the n queue, right? You just take those data into the stack itself. But when you are dequeuing, right? Dequeuing, you are putting this into the stack so that it is reverse, because you want to dequeue the first element, not the last element. You put this into the other stack so that this guy, say this is A, B, C, D, E, then it will be E, D, C, B, A, then you take it from there. So then it first in will be first out. So that is first one approach. When you are enqueuing, you just put it into the stack. When you are dequeuing, always you are put it into the stack and take it from there, right? Preserving your original stack. So the second approach is when you are enqueuing, enqueue, you put it into the yeah, when you are enqueuing, yeah. So the second approach is when you are enqueuing. Now you already have the data. You already have the data stack and data stack. You keep everything into the other stack. No, you keep, yeah, you enter your data into the empty stack, then keep everything into this stack and again put it back, right? Then again put it back. No. So what you're supposed to do is first when you're enqueuing, take everything from this stack to this stack, right? This stack. Say this now it is having something like A, B, C, D. You take it like D. Say you are having. I will explain from the second approach from beginning. Now say you are enqueue in the first element A. Now your other stack is anyway empty. Therefore nothing to put it to the second first stack. You just enter your A here. Then you put from there you enter into the other stack. Now your stack has only A. Now you are enqueuing B. Now again you are taking from this stack to this stack. Now A will be here. Now B will come on top of it. Now we are putting it back here. Now therefore it will be B and A and B and A. Now the last in is always top now. Now we are entering C, enqueuing C. Now again you are taking from there A, B there. Then you are putting C here. Now we are putting it back. Now it will be C, B and A. Right? So when you are doing D, again you are taking from there to there, therefore it will be A, B and C. Now we are putting D and you are putting it back, therefore it will be D, C, B and A. When you are taking or dequeuing, you can simply dequeue. Right? So when you are enqueuing, you are doing that effort. When you are dequeuing, you are just simply dequeuing. So that is the second approach. In the first approach, when you are enqueuing, you are just entering it to the stack. But when you are dequeuing, you are doing this swapping. Right? Put it to the other stack and take it back. Right? So you can implement whatever the approach. Right? So that question was repeated in 2019 paper as well, if I remember correct, or 19 or 18. So you just have to write that particular logic. Okay. So that is what they are doing. So this is they are doing it for uh, enqueuing they are just pushing, but dequeuing they are putting it to the other stack and from there giving you the answer because that is the easier approach. Okay, so you can just go through because I did this explain this in the last class as well. Okay, for the 2019 or 18 paper. Okay, but it looks like it's a very famous question for the popular question for the or favorite question for the examiner. I think this is the second time. Right. So next one. One wants to add 423 with 3867. If one use 3 stack up to perform, so this question has been repeated again, right? So what you are supposed to do when you are adding two numbers, you first put this into stack, right? You first put 423 into stack, so that therefore it will be 4, 2, 3 in the stack. You put that also into the stack. Therefore, the second stack will be 3, 8, 6, 7. Okay. Now you take pop one from each. There you will get 7. There you will get 3. You add those two and push the result to the stack. So in this case, 7 plus 3 is 10. 10 means you push only the remainder 0. Right? So 0. That carry you have to keep in a separate place. Right? Now 7 and 3 is gone. Now again you do the same thing. Now 6 and 2 will come and the remainder is also there. You have to add all 3 and again 6 plus 2 is 8 and 9. So that will be you are pushing that also there. There is no you are not carrying anything. Okay. Then you have to do it again. Now 6 and 2 is also not there. Now 8 and 4, that is 12. There is no carry. 12 means 2, and there's a carry, right? There's a carry. So next time from there you will be getting 3. If there nothing, you have to say 0. There's carry. 3 plus 1 is 4. Right? Now we are done. Nothing to pop from here, nothing to pop from here. That means we are done, right? And there is no remainder also. So therefore the stack is having something like this. Now you have to pop it again. It will give you something like 4, 2, 9, 0. Right? So 7 plus 3 is 10 means 0. 6 plus 2 is 8 and 9. 8 plus 4 is 12 means 2. 3 plus 1 is, right, 1. 3 plus 1 is 4. Right? So that must be the answer. I think this answer is wrong. Right? So if you feel like my answer is correct, you can always post it, your clarification. I think this answer is wrong because it says if one uses 3 stack to perform the above addition. Of course, I am using 3 stacks. This stack, and the answer stack. Okay, so this question has been given so many times in the past, but those answers were correct, but it looks like this answer is wrong, right? Maybe the examiner has messed up with this data. Okay, oh, right. Anyway, if one uses 3 stacks to perform the above addition, what would be the top elements in the resulting stack at each intermediate steps during the addition? Right. So this is the resulting stack. At each intermediate stage, it must be 0, 9, 2, and 4. So I don't know how these things came, right? It looks like the answer is wrong. Okay, right. So let's move on. So if you feel like this answer is correct, if you find the method, maybe there's a different way of using 3 stack, but I'm pretty sure answer should have been this one. Okay, because this question they have asked previously also. They have used this particular approach for those. Yes. Okay. Right. When performing the addition, one uses single integer variables to store the remainder. Of course, right? So that single integer remainder, right? So remainder also we add. Remainder also we add. So remember we keep that remainder there and we pop 2 and also add those pop 2 values and the remainder. Okay. Right, now let's see the question. What would be the remainder value at each intermediate steps? So again remainder values what we got is here it's 0. Sorry, here it is 1, 0, 1. And this says 1 1 1. Definitely answer is something wrong with the answer, because this is wrong means this answer is not what we get means definitely this is also not what we are going to get. Okay, so it looks like the two answers are wrong, but anyway, if you feel like there's another way, you can just comment on that. It looks like the answers are wrong. Okay, right, so next one is a easier one. So that's circular queue, right? So this is the front and this is the rear. So when you are dequeuing, you are dequeuing from the front. You are enqueuing, from the rear, or you are enqueuing to the rear. Okay. Now let's see the question. It's a very straightforward question. One wants to delete a node from the above circular queue. That means dequeue. What are the parameter values front, rear, and count after the deletion? So after the deletion, you are deleting from the front. So therefore, now your front is going to be not 0, front is going to be 1 because 10 is out. Your rear is not going to be changed, it's going to be 4. And it's still going, now this is front is 1, rear is 4, count is going to be 4. 1 4 4 1 4 4. That is a very straightforward question. I don't know why they are asking that kind of simple questions. Right, so the D. Write a Java code or pseudocode algorithm to search a particular item from the following single linked list using the following diagram to answer the question. So that is very straightforward. You have to start with the head, right? So and you have to keep moving while checking whether the value you are looking for is. So say this is your search method. There's a method called find. Find. You have to given the head, or if it is a class, it will be an instance variable. Say node head and what you are looking for, right? So in this case, it looks like a char jd. Right? So then you just have to write your code. You have to start with say node start, which you can initialize it to h, right? Or you can just start with h to h. So you can go for never ending loop like while true if h dot data, right, h dot data equal d, you are done. You can just return the whatever the value, right? Else you have to say that h equal h dot next. That means you are moving forward. Now your new h is here. Next time new h will be here, right? So you have to keep doing this until your h. So rather than true, you can say as long as h is equal to null. So that's anyway we did this in the class, and the code is available in the website, right? So as long as h data is sorry, as long as h is not equal to null, you can keep doing this. You are going to check whether the h dot data is equal to this d, then you are done, or else you are just making it go to the next level, h equal h dot next, something like that you have to write. Okay, right. So yeah, so it's explaining exactly like, so while the current node is not null, so that is what I wrote. And you have to make sure that current equal current next, etc. Right, write a Java code or pseudocode algorithm to find the length of a single linked list. So the same thing, you have to start from here. You have to go as long as your h is null, but you have to maintain a counter variable that you have to keep incrementing each time. So same thing as you're searching, but searching you return. Here you don't return. And you have to write the code. Say this is int, returning int value, and let's say the method name is, let's call it count, and you have to give me the head node, let's call it h. This is very straightforward. While our h is not equal to null, h equal h dot next, and make sure you have variable here int n or whatever equals 0. Now here you say n plus plus. Now as long as this loop is executing, every time n will be incremented by 1. When you are getting out of the while loop, that means your new edge is now null. You have come to this place. Now you can return your n. Return your n. So that n will have in the number of nodes here. Number of nodes here. Right? So that's it. So that is not a difficult question if you are okay with the basic object-oriented concepts. So you need to have count variable, which is as long as current is not equal to null, you are pushing it to the next level, current h equal h dot next or current equal current dot next. So finally you are returning the count or the n or whatever. So same logic is there. Okay, right. So those are very simple questions, as if you are familiar with object-oriented concepts, and of course the theory behind the linked list. Right, so then they are asking you to create a question about AVL trees. Uh, so if one insert the following nodes to the above tree in the following order, how many single rotations and double rotations are needed? Right, so this is your tree currently. To that you are supposed to insert. I think I did this. Yeah, not this one. So it will take a little bit of time anyway. So let's copy this. So it asks how many single rotations and how many double rotations are needed. That is not a difficult question, very easy question. Right, so now we have already some data. First we are supposed to add 14. Okay, first 14. So how to add 14? We have to preserve the shape property. Right, we have to preserve the shape property. So therefore 14 will go to here, 14. Right, now you have to check whether it's not balanced. No, it's still balanced. Now you can see these are the balance factors. It is still balanced, so therefore we are done with that. Then we have to add sorry, no, I made a mistake. This is a binary search tree, right? Sorry. So 14, let's see where the 14 must go. Right, yeah, 14 must go where? It's a binary search tree. 14 is greater than 13 but less than 15, so therefore 14 will come here. But it is not violating the balance property. Still, this will be balance factor is still. Now balance factor will be actually be better. Balance factor is 0 now. Therefore, no issue. Right? Now let's add 3. So 3 will go less than 13, less than 10, less than 5, less than 4. 3 will go there. Now we have to check whether the balance factor is violated starting from here upwards. Here it's okay. Here it's okay. Now balance factor will be 1. But now here there is a balance factor is wrong. Now this is 3, this is 1. Now the balance factor is 2. Right? Balance factor is 2. So therefore now it is not balanced here. And you can see this is a left situation. Left situation. Left situation. So therefore a single rotation is going to work. Single rotation is going to work. You have to rotate through this point. Okay. So let's do the rotation. So this is where we are going to do the rotation. And it's going to be single rotation. Okay, so then it will be 13. This side is not, we are not going to touch. 14, 16, 10. Sorry, 10 is going there. 10 is going there. 10 goes there. No, rotation must be here. Sorry, not there. Sorry, I made a mistake. Yeah. So rotation is rotation must be here, right? So 5 will go up, 5 will go up, then 10 will go down, 11 will also go down, right? Then 4 will be here and 3 will be here. Remember, this 6 has to be connected to the right side of the 10. Now we are done. Just one single rotation. Okay, just one single rotation. Now it is balanced. Now it is balanced. Now here the balance factor is again 0. Again 0. Now let's try to add the 45. Now remember, one single rotation is there. Okay, now let's add 45. It's more than 13, more than 15, more than 16, so the 45 is here. Now let's see whether the balance factor is violated. Here okay, here okay, here also it is okay, here also it is okay, fine. Now let's add 7. It's less than 13, more than 5, more than 5, less than 10, uh, greater than 6. So that means 7 will go there. Now let's see whether it's violated. Whether it's violated. This is okay. This is okay. Here also okay. 1, 2, 3, 3. Right. So I think it's okay. Right. So just one single rotation is needed. Right. Just one single rotation is needed. So we just did a one single rotation there. If I made a mistake, you can just double check. It looks like one single rotation is needed. Right. So let's see the answer. I think the answer is completely different answer. Yeah, it says you need two single rotations, but it looks like you don't need two single rotations. Okay, now I'll do it again here. So I'm adding 14. 14 will come here, right? 14 will come here. 3, 3 will come here. Now it is unbalanced here because it's 1, 2, 3. 3 minus 1 is 2. Now I have to do a rotation. Now this is where the balance is violated. You have to do rotation here. So that means 13, 15, 16, 14, 5, 4, 3, 10, 11, and this 6 has to be there. Right? 14. So now 45 can be added. It will go there. 7 has to be added. It will go there. So no issue. Yeah, just one single rotation is needed. I don't know why. So we can double check using our tool lab also whether it's just one single rotation is needed, right? So according to my answer, just one single rotation is needed. Okay, now let's use our online tool. Actually, I did that in the morning. Where is the AVL tree? Right, so this is the AVL tree. Let's create an AVL tree and see. Create empty. Okay, insert 13. Then 10 and 15, 10, 15, 5, 11, 16, and then we have to add 4 and 6. Yeah, 4 and 6. 4. Right, now let's see whether any after this. So that is the question they have given this particular binary tree. Now let's add the given things and see how many rotations. 14, 3, 45, 7. 14, 3, 45, 7, right? 14. Now look at the things. 14 added here. No rotation. No rotation. Still no rotation. Now let's add 3. It will come here. And now there will be rotation here. This is where the issue. Right, rotation. You can see just single rotation. Right, one rotation yet. One single rotation. Just one right rotation. Now, which one we added? 3. 3. Then we have got 45 and 7. So there won't be any rotations. 45. It will be added here, and there won't be any rotation. No rotation. Still just one single rotation. Final one is 7. So 7 will be added here, and there won't be any rotation. Checking, 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 nothing. So you can see just single rotation is needed. Definitely the answer is wrong in the answer sheet. The answer sheet answer is definitely wrong. We double check with the simulation as well. Okay. So what we got is correct. We just need just single rotation. So we just need one single rotation that happened here. That's it. Okay. So our answer is correct. So this must be one single rotation, no double rotation, right? 1 and 0. Right. Construct a BST or binary search tree using the following given number. That is a very straightforward thing. Right. So you just have to keep inserting the creating the binary search tree. Okay. So that means 7, 4, 12, 3, 6, 8, 1, 5, 10. So that must be the answer. So those are straightforward things. Yes, that's it. Then what they ask? Write a recursive Java code or pseudocode algorithm to find the minimum key value. So minimum key value means from your head you have to keep moving left side. Keep moving left first. That means you have to keep moving right, left child, left child, left child. Right, right. So you have to write like that. So you will be given the, so it's say find min. You will be given a node type which is your root. Then what you are supposed to do is while your root is not equal to null, you have to say root equal root dot left child. You have to keep going like that, right? Then of course every time you have to keep the root dot data value here. Then once you get out of the while loop, you can return that. So that's it. So we did that in the class. So it is using the recursive approach. So the recursive approach, or you can go for the loop approach. Right? So, but you have to go keep moving for left side, right? Left side. So that is why when it's calling itself, it is saying call itself for the left child. So this is a recursive approach. What I wrote is the normal loop approach. Right? So it's easier to remember the loop approach than the recursive approach. Okay. Anyway, both are going to work. Right. So the next question. T is a min heap of height 3. What is the largest number of nodes that T can have? What is the smallest number? Right. So T is a min heap of height 3. So min heap means smallest value is here, then the larger value. Height 3. What is the largest number of nodes T can have? So remember it's a heap. You have to preserve the shape property. That means it must be something like this. 1, 2, height 3, right? Height 3. So still the height is 1. Now it's, because remember it has to feel like this. Now height is 2. Now this is height 3, but this is, yeah, this is okay. This is okay for the heap. Now this is a heap of height 3. Level 1, 2, 3. What is the largest number of nodes that T can have? What is the smallest number? So the smallest number of nodes is this. That is 1, 2, 3, 4, 5, 6, 7, 8. So the smallest number is 1, 2, 3, 4, 5, 6, 7, 8. Right? What is the largest number? So the largest number is when everything is filled. This is filled, this is filled, this is filled, this is filled, this is filled. Now that is the largest number. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15. So the largest number is 50. So that means 8 and 50. Right? 8 nodes. Right? Largest number is 15. So the largest is 15, smallest is 8. Correct. Okay. Right. Show the result of running the partition subroutine of quicksort on the following array. Now again it's a quicksort, but I think for this one the previous logic is not going to work. Right? Let's do and see. Let's do and see. Okay, so let's do the logic that we did previously. Right, so I'm going to use this array itself. Right, so this is the pivot. This is the pivot. Now what is the logic? uh, so we have to start from the left. Our small is here, our left, so start is here, our end is here. Then we have to move start leftwards, move end, move start rightwards, move end leftwards. So start, we have to keep moving left as until you find a value bigger than your index pivot. Okay, bigger than pivot. So 23 is not bigger than pivot. Anyway, we can start from here. 2 is not bigger than pivot. 35 is bigger than pivot. Yes. Therefore, this is your new start. Okay, new start. Here you have to come until you find a smaller value than pivot. So 22 is smaller value than pivot, right? Because pivot is 23. Now you are done. Now this is your end. Still start and end has not crossed. Therefore, now we have to do the swapping. In that case, the answer, the value will be 100. 23 to 22. So I will write it again. 23 to 22, 27, 6, 17, 49, 49, 7, 35 and 33. Now my 35 is now replaced with 22. This is my start. Here the 35 is my start. N. Now still the pivot is this one. Now again I have to do the same thing. Keep moving right side until you find a value bigger than 23. Yes, I already found here. This is my new one. Here you have to come until you find a smaller value. You found it. You found it. Now again we are going to do a swapping. So that means 23 to 22 7 6 17 49 27. That is my end start. Then 35 33. Now again we are going to do the same thing. Come rightwards until you find a bigger value. 6 is not bigger, 17 is not bigger, 49 is bigger. So this is my new start. Then I have to come left side until I find a smaller value. 27 is bigger, 49 is bigger. Yes, 17 is smaller. 17 is smaller than 23. Now this is my end. Now you can see end and start has cross. Right? When you cross, you have to stop and you have to swap the pivot with the end, not the start. Pivot with the end. Now the answer is 17 to 22 7 6 23 49 27 35 33. But unfortunately that is not the answer here. That is not the answer here. That means either they have used a different strategy or the answer is wrong or whatever. Okay, so this must be the answer if you use the same strategy. The thing is there are so many tactics. If you insert into another online simulation, it might come up with some completely different thing, because there are so many ways to find this do this quick sort. Okay, do this quick sort. So you can see either the answer is wrong, or maybe it has they have used a different technique. Okay, for uh, that. Okay.
Excuse me.
Yeah.
Are we supposed to do all the partitioning, like from beginning till the end?
No, no, no.
Not
Only for one partitioning.
only.
That means only the value, that is the 23 must be in the correct position. That's it. 23
Oh,
must be in the correct position. But you can't just add these numbers arbitrarily. You must follow the proper logic, and according to the logic, these values will be there. Okay, so but we followed the
okay.
logic that we discussed last time, but now it
Okay.
is a different thing. That means they have either used a different strategy, or they have made a mess of the uh, algorithm and come up with the wrong answer. I'm not sure. Okay, right.
Okay.
Right. So, in the next question is, how many pivot values need to sort the above array. Now remember, every time you are making it to half, right? So therefore, how many pivots we need? So first time you take this pivot, right? Then it will be make it to half again, right? Make it to half. Now let's see, 23. And here, for to answer this kind of question, you don't need the exact logic. So now we know that all the values smaller than that will be left, right? The bigger than that will be right. So therefore, something like 2 6 7 22 will be here, but it will be in different order. 722, and here it will be 35 27, 17 will also come here. 35 27, 49 and 33 will be there. So that is one partition. Then again you will take a partition like this. Again it will be divided into 2. Right? Again it will be divided into 2. Here also you will take a partition. Again it will be divided into 2. So therefore how many pivots you will need? Uh, say something like, again it will be divided into 2. Again it will be divided into, again 2, 2, 2 and 4, 5, 6, 7. I think you need 6. 1, 2, 1, 2, 3, 4. Here two partition is going to work, but here there is a 3 and 2. Again you need 2 and again 1. 1, 2, 3, 4, 5, 6 will be needed. Right. So here just 2 more pivots will do. Here not 2 more because there is 3 data. Therefore for that you need another partition. 1, 2, 3, 4, 5, 6. Okay. So 6 pivots will be needed. Right, so we'll stop at this point. We'll continue with this. Okay, just one more question, right? Right, so this is a merge sort question. So that you must be able to do. So this is just they are explaining the merge sort algorithm and asking you to show how the merge sort is going to work. So that you know how to do that. You separate it. You keep separating it, right? So this is your original data. You separate it once. Right? You separate it once, right? So that part and that part, then again you separate it from there. Separate it from there. If it is odd number, you can take 2 or 3 or 3 or 2. You keep separating until you get into 2, just 2 of data. uh, Here also you have to separate it again, right? Then you only sort these two data, like 54 and 26. You have to swap 26 come here, 54 come here, 17 come here, 97 come here, likewise. Then you keep merging from bottom to top, right? So then you come from bottom to top, then it will be sorted, right? So I think they have only mentioned you to show the partitioning, not the sorted part. So that's it, right? So they haven't asked you to do this swapping, right? Do this swapping. Here you need a swapping, here you need a swapping, here only one data, here you need a swapping, then you have to keep merging. So merging part they haven't asked, they have asked you to just draw the partitioning only, right? So you just have to keep partition by half. Okay, so we did the 2017 paper. We'll do another one more session to complete the 2016 paper. Okay, we'll stop at this point. So if you have any questions, you can just ask in the WhatsApp group. Okay, right? So any other questions you have? Right, so then we'll stop at this point. Okay, right, so thank you.